And lastly, if we're talking about a molecule that has more than one central atom, which is what we're very, very often doing, you need to deal with each one separately. So for example, with methane or methanol here, we have a carbon, which is a central atom, and we also have an oxygen, which is a central atom. You need to talk about the geometry separately. You don't talk about the geometry of the entire molecule. So let's go ahead and look at some of these VSEPR examples, and Professor Drennan is going to help demonstrate what some of these are with some models here. So the first case we're going to talk about is without any lone pairs. This is the most straightforward case. And our first case that we can have is AX3, which is going to have a linear shape. And that will have a bond angle of 180 degrees. The next case that we can talk about is trigonal planar, or AX3. Now, you do need to know these geometry. You need to know the names. A lot of them are very easy to remember. I expect not too many of you will get linear incorrect. Also, trigonal planar, pretty easy. Trigonal, it has 3 atoms around the central atom, and the molecule is planar.
So what is the bond angle for this geometry? 120.
All right, great. So next we can think about AX4. And this is what's called a tetrahedral geometry. If you're trying to remember this name, you can think of each of those bonding atoms as being in the corner of a tetrahedron. One thing I want to point out is you're seeing some notation we haven't used before in this class, where you have a wedge coming out at you, and you also have a dashed line to one of those bonds. Anytime you see a wedge in a Lewis structure, it means that it's coming out at you. It's either coming out of the screen or it's coming out of your paper. And anytime you see a dashed line here, which might be easier to see in your notes, that means that the bond is actually going into the page or into the screen or into the blackboard.
And what are the angles for tetrahedral?
All right, so they're 109.5, pretty close. So that's as far away as those bonds can get from each other, would be 109.5 degrees. The next case we have is AX5. That is what we call trigonal bipyramidal. Again, we have trigonal because we have those 3 bonds in the center. And if you can picture putting walls between all those bonds, you can see there's a pyramid on the top and a pyramid on the bottom, so bipyramidal.
And there are 2 sets of angles here. What are the angles for the equatorial atoms? 120.
Right.
And then for axial, 90.
And again, axial, those are just the ones in the axis, and equatorial if you picture a globe around the equator. So the last case we have is AX6. This is, axial there. AX6 is what we call octahedral. You can picture each of those bonded atoms as a corner of an octahedron.
And what are the angles in this? There's 1 set of angles. 90.
Yep, great, so 90 degrees. All right, so this is all straightforward when we're just thinking about different molecular shapes that don't have any lone pairs in them. But once we start having lone pairs, we now need to think about how those lone pairs are going to affect the geometry. But before we do that, let's talk about some examples of molecules without lone pairs. So the first case is what we saw at the beginning of class, carbon dioxide. And we said that that was linear, and now we know why it's linear. It has a formula of AX2 and an SN number of 2.